Let's talk about approximating the area under a positive continuous function. You got to recall some summation notation. We're going to be using this today. Our objectives is to use summation notation to approximate the area number, or what I call the accumulation number, underneath a positive continuous function. We're going to approximate the area number, or the accumulation number, under a positive continuous function with left endpoint, right endpoint, and midpoint Riemann sums. And you want to understand when you overestimate or underestimate. In integral calculus, we are intrigued about finding geometric areas. For instance, if you had a function that represents a semicircle, we know it's a continuous function and we want to be able to figure out the area underneath that semicircle. And you even know the area formula for such a geometric figure. However, not all functions are semicircles. In fact, many functions are continuous. They might even have sharp corners. And we know there's an area underneath that function that reaches the x-axis. Our goal today is to approximate this area, and we'll use something called a Riemann sum. Here is the definition of a Riemann sum, and we typically study the first few sampling points. And those sampling points include a left endpoint Riemann sum, a right endpoint Riemann sum, or a midpoint Riemann sum. Now at first these formulas look daunting, but our rectangles are usually few. We're not going to draw too many rectangles. Let's go ahead and begin with an example. Let's write both left and right Riemann sums for this function here on the interval 1 to 5 with 4 rectangles to estimate the area underneath this continuous function. Which sum is going to be an underestimate? So we're going to apply our algebra skills, and in this case specifically graphing. Now I'm going to use NTS. NTS stands for not to scale. Draw some ordered pairs here. And there is our function on the interval 1 to 5. Now, if we're looking at a left endpoint Riemann sum, we simply draw rectangles starting from the left endpoint. Since n equals 4, it's not difficult to draw these rectangles. Now clearly, if you shade in those rectangles, we actually have an overestimate of the area. Let's go ahead and write the left endpoint Riemann sum. We do need delta x, which is a formula. Now all we're doing is adding up many rectangles. So if we look at the function height as the length, and we could see the delta x is our width. So the delta x is the width of a rectangle, and the height here is the function height. So we're going to do length times width many, many times. And we know we have 4 rectangles, so we should have 4 terms. And if you write this in summation notation, you're going to realize, oh yeah, that is, in fact, our left endpoint Riemann sum. We need a common denominator of 12. And there is our overestimate of the area. Let's go ahead and do the right endpoint Riemann sum. And I'm going to use the same picture. I'm going to start on the right endpoint and draw a rectangle. Start at the right endpoint and draw a rectangle. Start at the right endpoint and draw a rectangle. Start at the right endpoint and draw a rectangle. And this time I will actually shade these right endpoint rectangles. And you can see that this is an underestimate of the actual area underneath this function. How can you see an underestimate? Because we have a gap right here. We never accounted for this gap here, and this little gap here, and there's a little gap here, and a little gap here. So we know this is an underestimate. Let's go ahead and write our right endpoint Riemann sum. I'll use capital R with a subscript of another R to indicate the right endpoint. Notice our greatest common factor is delta x. This time our common denominator is 60. And like I said before, this is an underestimate. Let's look at a different continuous function. Let's explore a trigonometry function. This is our typical cosine wave, but our interval is from negative pi over 2 to pi over 2. We'll use our trigonometry knowledge here to draw a rough sketch. But this rough sketch does need a little bit of accuracy here. I'm going to use NTS for not to scale. Now we got to fit 6 rectangles here using a left endpoint. So I'm going to just divide my function into 6 subintervals, and I'm going to draw a left endpoint. There's my first left endpoint rectangle. And then from this left endpoint, I'm going to stretch to the right and draw another rectangle. And then from this left endpoint, I'm going to stretch to the right and draw another left endpoint rectangle. These first 3 rectangles are underestimating the area. What happens when I land on the y-axis and draw this left endpoint rectangle, then draw another left endpoint rectangle, and then finally we have one more left endpoint rectangle right about there. And notice those second 3 left endpoint rectangles are now overestimating the area. It's overestimating. As you can see, it covers up more space. That's an overestimate. Now, how do we get our sampling points? Well, we know our delta x. Delta x is just a formula. And we get our delta x to be pi over 6. Now we already know our first left endpoint. Our first left endpoint is actually x sub 1, which is negative pi over 2. To get to our next endpoint, we simply add delta x. And we do this in a systematic manner. We just add delta x to every single left endpoint. I should say we add delta x to the previous left endpoint, and we'll get all our left endpoints that we need. We are ready to write our left endpoint Riemann sum. We know our delta x is pi over 6. And we're left with evaluating our common angles. Once again, you're using your expert knowledge of trigonometry. You have your trig values already memorized. There's no need for the use of a calculator. You got this. Common angles with common trigonometric functions are just known facts. You have to just know these things, and then that will help you improve your study of calculus. Notice you get a common denominator of 12. And we finally get 2 plus root 3 times pi over 6 is our estimate for the area underneath this continuous function.